All right, so let's continue with the lecture from last week. Okay, chemical elements continued, and I don't remember why I did this slide here. It looks like it's just a it looks like it's just the periodic table, the left side where we have the alkali earths, the alkali metals, the alkali earth metals, and we have some transition metals here. I guess one thing to note is that here is what a block from the periodic table looks like. We have the name of the element, which is uranium here, radioactive, by the way, right? Not radioactive. Is it not radioactive? Nuclear, by the way. And then the atomic number here, which is 92. The atomic number is the same number as the number of protons, right? And in an element that is uncharged, it's also the same number as electrons, right? And then the symbol here, U for uranium, is the symbol. And the atomic weight is actually the number of protons plus the number of neutrons, okay? The number of protons plus the number of neutrons in the nucleus is the atomic weight, right? Um, and then the other thing to note too, yeah, the other thing to note too is like a lot of these elements, for example, some of them have symbols that are very reminiscent of their names, like uranium, U for uranium, but things like sodium have Na, which is kind of weird. You're like, what is that? What does Na have to do with sodium? So the Latin word for sodium is actually natrium, and that's why it's Na. And there are a few other ones like that too. Oh yeah, for example, iron. Iron is iron with an I, but for some reason its symbol is Fe. So old school chemists call iron ferrous or ferric, which you knew that already from ferromagnetic, from the magnetism lecture, right? Hey, so um, so yeah, there are a lot of elements on the periodic table that have different symbols than what their names are, and we have that's because we have other people from other languages and other origins that name these things too, right? So remember, Mendeleev was a Russian. He named like half of these elements. So this is a very useful figure right here. Okay, so if you remember back from before our exam, I was talking about how elements all want to have a full outer shell, right? And when you're on this side, for example, uh, which I'm not when you're on this side, but this side right here, these rows right here, the period numbers show the number of shells there are, right? The n equals number, which is n equals 1, means that there's one shell. N equal 2 means there's two shells, and then n equals 3 means that there's three shells, right? And then so on. Uh, and so everything on the top row has one shell. Everything on the second row has two shells. Everything on the third row has three shells, right? And the reason why this is such a convenient little graph, which I haven't even seen these in the chemistry book yet, so in like an actual majors chemistry book yet, so this is very helpful. But it shows you how many electrons are present on the outer shell. So here with hydrogen, you see it has one shell and it's got one electron, right? Well, that alone means that it's not happy, right? Because to be a full shell at the first shell, right, you have to have two electrons, right? And how do you know that? Well, you know that because if you move over to helium right here, helium also has one shell and it's got two electrons, right? And it's a part of what we call, remember, the noble gases. And the noble gases don't like to interact with anybody because they have already 8 electrons in their outer shell. Chemical reactions and the process of making any kind of chemical or thing you see around you, uh, that is because electrons strive to have a full elements or atoms strive to have a full outer shell of electrons. And so in the very first n equals 1, the answer there is 2 electrons for an outer shell, right? For period 2 and 3, both of those are 8 electrons in their outer shell. Okay, 8 electrons in their outer shell. Okay, so over here we have sodium, which is someone said I forgot to put in the question about the cat. Dang it! But the kittens. But don't worry, I'll put it in the next test. Right? Remember I was talking about sodium right here. Sodium is quite dangerous. It's explosive when it's exposed to air. The reason why it's explosive when it's exposed to air is because our air has water vapor in it. Okay. And next Monday, I'll probably show you a really fun video of the explosions. I wanted to do the explosion here on this bench, but they said that I couldn't do it. Apparently, it's too dangerous. And plus, those tables on its last leg anyway. So explosions might not do well for the table. But sodium is quite the explosive molecule, explosive element because it has one extra electron. It's so close, right? It's super close to being 8. It just needs to get rid of that one electron, right? And so the way it can do it when it's exposed to air, right, in the water vapor, is it can just throw that electron over the water, right? And that's what causes the explosion, right? And then you get like sodium oxide, right? And so or something like that. And so that's why it's quite unhappy when it just has one electron to get rid of. So on the other hand, though, if we have a look over here at chlorine, right? Chlorine is also very dangerous in itself too, right? In World War II, no, sorry, World War One, Franz Haber, I think it was his name, Haber, used chlorine as a biological weapon against the Allies. And like I was saying before, last week before the exam, right? Chlorine is the element or the atom that will rip away an electron from a kitten, right? Because it just needs one more. It's got 7 electrons, right? It just needs one more electron to be happy, right? And if there's nothing around to give it an electron, it'll rip it out of your throat, right? It'll rip that electron out of the water in your throat and making it hydrochloric acid inside your throat, and uh, that's what they used as the biological weapons the Germans did uh, in World War One, right? So, but the fun thing about it is that if there's some sodium around and there's some chlorine around, and sodium wants to give up this electron, so he has 8, and chlorine, she wants to accept the electron because she wants to get 8. They can be a happy couple with each other, right? A nice little couple, right? A little pairing. That can happen all over the periodic table, right? Lithium can do the same thing with chlorine, right? Fluorine too, right? All these things are actually quite dangerous on their own, right? But you put them together and you get things that you can eat, which is pretty cool, right? It might be just be better just to be a noble gas, right? Oh, but so just to also mention as well, um, the diatomics too. Like for example, hydrogen, right? The diatomic H2 hydrogen can also be with itself. So some people, right? Some people like sodium and chlorine, right? They like to be paired up with someone different from themselves, right? But some other people or elements like to be paired with each other, right? They like to be paired with each other. So it's whatever floats your boat, whatever floats your boat. And for hydrogen, he, he wants to be with another hydrogen, right? And so let's see here. I think there's yeah, chlorine does it too. Chlorine can be can pair with itself too. So quite incestuous here, by the way. If you didn't know that, Group 7A is quite incestuous. Almost every one of those guys like to pair up with each other, right? Um, and so they're keeping it in the family in Group 7, right? But sometimes you can convince a Group 7 family member to break off and maybe pair off with somebody that won't be so genetically similar to them, right? That's genetically said that there's no genetics in elements. That doesn't make any sense. Forget what I said just said. But you know what I'm saying. You understand. Cool. See, I'm thinking genetics now because someone said something about heterozygous. My apologies. Um, anyway, so I already said this a second ago, right? The atomic. Oh no, I haven't said this yet. The atomic size of an element also varies periodically, the first periodic table, from 0.074 nanometers, which is hydrogen, to 0.747 nanometers, which is cesium. So right there's hydrogen at the very top, and there's cesium at the very bottom. And as you go down the product table, the atoms get bigger, right? The atoms get bigger, which makes sense because as you go down the periodic table, you get more and more electrons, right? And the more electrons you have, the bigger you get, right? So atom size increases as you go down a group, but interestingly though, atomic size actually decreases if you go from left to right. If you go from left to right, it actually decreases. Interesting stuff, right? So the atoms at the far left are the largest due to less charge, fewer protons in the nucleus, and the outer electrons are more loosely bound. So there's a picture here that's very uh, reminiscent of what I just spoke of here, right? So if I ask you a question about a periodic table on the exam, it might be something like this, where I'm asking you which is the bigger element, that type of thing, right? And really all you have to do is look at the periodic table to tell me, because things that are over here, like on this corner, are what? Super small, right? But things on this corner are super big, right? And it literally gradually gets smaller as you go across, right? So that's a relationship you need to know. Atomic size gets bigger as you go down a period, but atomic size actually gets smaller as you go across a period. Okay? Everybody clear on that? That will be there will be an exam question that is very similar to what I just said. Okay? So here is a question. The first question of the day. As you go down a group on the periodic table, what happens to atomic size? Does it increase in size? Does it decrease in size? Does it remain the same? Or is it all of the above? Well, how is that even possible? Okay, I'm not going to check to see what the distribution is because I'm too lazy to log in. The answer is what? Increases, yes. Yes, atomic size increases as you go down the group on the periodic table. Okay? So that's one trend. So what we're doing right now is going through trends of the periodic table. Okay? The next trend is called the ionization energy. Okay? The next trend is called the ionization energy. And ionization energy, right, is the amount of energy that is required to remove an electron from an atom, right? To remove an electron from an atom, okay? Ionization energy increases across the period, right? And then due to additional protons in the nucleus, but then ionization energy goes down, decreases when you go down a group because the additional shells are situated between the nucleus and the outer electron shell, right? So the bigger the atom, as you go down the periodic table, the less ionization energy is required to remove an electron, which makes sense because the electrons are further away from the nucleus, so they're easily picked off, you know, right? Whereas when you're closer to the top of the periodic table, right? When you're closer to the top of the periodic table, the electrons are much closer to the nucleus, which is very attractive. The attractive force of the nucleus, because the protons in there, makes it a little bit harder for you to remove a proton, an electron, right? So here's a little graph here, not a graph, but a what's it called? A graph? No, a diagram. Here we go. That's what it is. So here's a little diagram here, right? And it shows you that ionization energy decreases as we go down, right? A group, right? But as we go across a as we go across a period, right? The ionization energy increases. Okay, so this makes a lot of sense too, because remember over here, these things like chlorine, for example, they have a lot of electrons already, right? 7. They just need one more to fill up its shell, right? If you take one of its electrons away before it gets that electron, what happens? Now it needs 2 electrons to be happy, right? So it's going to hold on to that 7 as tight as it can so another chlorine comes over and shares with him, right? I mean, if that's the way they want to be, but sodium could do it too, right? The sodium could do it too. So it makes sense, right? When you're up here, especially with the noble gases, are those noble gases going to want to get rid of an electron? Heck no, they're already happy with 8, right? And then these guys here, the halogens, right? They're only missing 1 electron. The chalcogens also only missing 2 electrons. They only need a couple to be whole again, right? To be whole. And so they're not going to want to give up any electrons because it makes it harder for them to complete themselves, right? And then sodium can come over and can complete chlorine because sodium is quite readily wants to get rid of its electron to give to chlorine anyway. So sodium's like, yeah, yes, please take my electron, please take it, right? Which is perfect because sodium and chlorine are in a very typical give-take relationship, right? Sodium does the giving, chlorine takes the taking, does the taking, right? So anyway, so remember, ionization energy increases across a period and then decreases as you go down a period. Go down a group. Okay. So let's talk about chemical formulas real briefly, right? In order to easily and conveniently discuss chemistry, we can use chemical formulas. Chemical formulas are written Chemical formulas are written by putting element symbols adjacent to each other, usually with the metal first, right? And then a subscript following each symbol designates the number of atoms. So some compounds have special names. So we already talked about one ad nauseum already, which is sodium chloride. Sodium is the metal, so the sodium goes first. Chloride is the nonmetal, so it goes last, right? Those are called ionic compounds. But here are some more examples, right? Here's water, of course, right? But if you wanted to call water by its chemical name, you'd actually call it dihydrogen oxide, right? And then you guys know what hydrogen peroxide is? The stuff that people used to put on wounds, and it bubbles up, bubbles up. That stuff, right? That's actually H2O2, right? And it's called hydrogen peroxide because the prefix per in Greek means one extra, right? So that's why it's called hydrogen peroxide because it has one extra oxygen there, right? We have a special guy here named ammonia. We use that to wash our windows. I've talked to you about that before. It's in Boondock Saints when William Defoe was trying to, get that blood or whatever it was. Very bad forensic science, but whatever. Methane right here. Methane is the same thing that runs through your gas lines to make your stoves, right? To run your gas stoves. I mean, if you haven't used a gas stove, I highly recommend it. It's awesome. You can get the heat perfect, right? Just perfect flames. You know, my mom has an infrared stove, and though it sounds cool because it's infrared, she only has like high, medium, medium low, and low. But I can make my heat exactly the way I want it, right? So, because sometimes you got to go in between medium high and high, right? I don't know why I'm even talking about that. Anyway, we have nitrous oxide and we have nitric oxide. I can't remember what one of these things causes erections, right? I think it's actually NO, nitric oxide, and I think nitrous oxide is actually laughing gas. Nitrous oxide is laughing gas, and nitric oxide is what causes erections, right? Hydrochloric acid. Hydrochloric acid. That's just an acid, of course. Also known as muriatic acid. Has anybody ever watched that show on Discovery Channel called Whale Wars or whatever it's called? I can't remember. It's the one where there's this ragtag navy is a group of people, and they're going after people who poach whales. Anybody ever heard of that before? That must be before my time, before your time too. No, well, the only reason why I mention it is because since they're kind of like a ragtag navy, they're not like a real navy. They're just a bunch of civilians that can't use weapons. So their weapon is actually a bottle of hydrochloric acid, and so they just like as grenades, they throw the bottles of hydrochloric acid at people. So it's a little crazy. They call it muriatic acid, but it's hydrochloric acid. They claim that the reason why they do that is because they're not trying to hit people with the hydrochloric acid. They're trying to hit the whales, like the ones that they've caught and killed on top of their ships. And so when they hit the whales with hydrochloric acid, it spoils the whale meat. And so it makes it so that the poachers don't want to get the whales anymore, right? But apparently that's a big problem, whaling, poaching. You know, you guys have no idea what I'm talking about, do you? That's all right. That's all right. That's okay. It's okay. Okay, so we have nitric acid here, also a strong acid. Oh, both of these are very strong acids. Acetic acid. Well, everybody knows what acetic acid is, right? That's vinegar, right? Vinegar. Okay. You add some vinegar to some baking soda, and it makes a lot of foam, right? That's those fake, volcanoes we see on TV, right? More importantly, you can actually have apple cider vinegar, right? Uh, and uh, and then you can add some like bacon or something in it, or even dead fish or shrimp, and then put like a lid on top of it, and it's a great fly trap. If you're wondering how to get rid of flies, because apparently flies love that kind of stuff, right? Add a little sugar, get some ants in there too, but maybe you don't want that. Sulfuric acid, another very strong acid, right? Carbonic acid. So, if you didn't know this, carbonic acid is actually very prevalent because we have carbon dioxide in the air, and we also breathe it out. Contrary to the belief of some FedEx employees. And so, what happens is that the carbon dioxide will actually dissolve into water, and make the water slightly basic, slightly acidic, because it becomes to carbon dioxide becomes carbonic acid in water, and so that actually has a lot of health implications because your blood is actually has to be a very certain level of acidity. Specifically, your blood is a pH of 7.4, and the way that your body maintains that 7.4 pH, right, is by employing this thing called the carbonate bicarbonate buffering system, right? Your liver does it for you, right? And I think it's your liver and your kidneys. Sorry, I'm not a doctor, not a medical doctor, so I think it's your liver and your kidneys, and it goes back and forth between making carbonate and bicarbonate so that your buffer, your blood is in a homeostasis, right? It doesn't like your blood doesn't get too acidic, which is bad. Phosphoric acid here, another strong acid. Um, I so whenever people ask me to spell my first name, which is Fong, it's Phong, and so like I say it's Phong, and people would think it's spelled with an F, and I'm like no, it's Fong, like phosphoric acid, like pH, and then so it's funny because Marla heard me say that one time, and then she goes, why didn't you just tell them it's like phone? Like that's easier than saying phosphoric acid. Phosphoric acid is like 5 syllables. Phone is like 1 syllable, and it sounds like your name. I'm like, oh, good point, babe. That's a very good point. So, but yeah, I used to tell people, oh yeah, you spell my name like phosphoric acid. It's great. Anyway, so there's these things called binary compounds. Very simply, what is a binary compound? Binary means two, right? Or bi means two, and then nary means um, I don't know what nary means. Bi just means two, right? And so when you have a binary compound, things like sodium chloride have two elements in it. That's a binary compound. Aluminum oxide, two elements, right? Calcium nitride, also two elements. Those are called binary compounds. Okay, those are called binary compounds. So the interesting thing here is that if you have a binary compound, you always start out with a metal like sodium, and you always end it with "ide." So this is supposed to be chlorine, right? But since it's a part of a binary compound, we call it sodium chloride. As simple as that, right? Or aluminum oxide here. You could be really, weird and say aluminum oxygen, but that doesn't sound cool. So you say aluminum oxide, right? Cool, cool, cool. So your next question here: which of the following is not a binary compound? Sodium chloride, aluminum oxide, calcium nitride, or potassium phosphate, like my name. Dang, I forgot to bring my drink. No wonder I'm getting so parched. I'm too lazy to log in to see what the distribution is, so I'll give everybody a few minutes to sign on for attendance purposes and participation grade purposes, and then we can talk about the answer. Aren't you guys excited about chemistry? It's so much fun, right? Look at the sign. I love chemistry. You should all love chemistry, right? It's so great. So great. I'm happy to see that none of you signed up for this class next semester. That means that you think you're going to pass the class, so that's good. I only say that because in one of my other classes, someone has already signed up for the same class next semester. So with me, but I will say that person is going to have a huge advantage over everybody else because they've already taken me once before. Um, all right. What does everybody think? What's the answer? D. Yes, D. Potassium phosphate is definitely not the binary compound. It's got a threesome going on, right? It's got a threesome going on. All right. So here's some other compound names, right? We always go. We have bromine. It becomes bromide. Chlorine becomes chloride. Fluorine becomes fluoride, like fluoride toothpaste, right? Hydrogen becomes hydride. Uh, uh, what is? I was going to say something about hydride, but I can't remember now. Iodine becomes iodide. Nitrogen becomes nitride. Oxygen becomes oxide. Sulfur becomes sulfide. Good stuff. Good stuff. Okay. So we name compounds with two nonmetals a little differently. Okay. So the more metallic or less metallic element is, the further to the left or the down the periodic table is usually written first, and then the formula and then is named first. So the second element is named with an "ide" again. So Greek prefixes are used to designate the number of the atoms in the molecule, right? So when we talk about the Greek prefixes, we're talking about mono for one, right? Actually, I'll just show you the. Oh wait, there we go. So mono means one, right? Di means two, tri means three, tetra means four, right? And then penta means five, hexa means six, hepta means seven, octa means eight, nona is nine, deca is 10, and so on, right? Does anybody know what 11 is? Just out of curiosity, does anyone know what 11 is? It's undeca, right? Undeca. And then 12 is dodeca, right? Interesting, right? Those Greeks. Very fun. Very, very fun. Anyway, so here we have hydrogen chloride, right? Remember I was talking about hydrogen chloride gas becoming, or chlorine becoming hydrochloric acid in your lungs, right? That's what hydrochloric acid is before it becomes an acid. It's actually a gas, hydrogen chloride gas. And then we have carbon disulfide because it has two, right, sulfurs. Phosphorus tribromide because it's three bromines, and then iodine heptafluoride, right, for seven. So the thing that you need to know is that when you have a metal with a nonmetal, right, you always say the metal's name and then you say the nonmetal's name and end it in "ide." But when you have a nonmetal with a nonmetal, right, you always have the nonmetal's name, and then instead of doing just the "ide" part, you have to put the Greek prefix on there too to tell you how many of the nonmetal there is. Okay, right? So, for example, right, sodium chloride, right? I'm not saying sodium monochloride. I'm just saying sodium chloride, right? Because that's a metal with a nonmetal, right? But here it would be carbon disulfide because it's a nonmetal with a nonmetal, right? The only one that's a little confusing is hydrogen because hydrogen is on the left side of the periodic table right here, right? But notice that it's red. It's like the only thing over on the periodic table on the left side here that's not a metal, okay? So it's just like that Super Troopers thing I was talking to you about before, right? That little guy, don't worry about that little guy. He's a nonmetal, right? He's a nonmetal. So then we have polyatomic ions too, right? Ions are basically atoms or chemical combinations of atoms that have an electric charge, either positive or negative, right? And so remember, chloride has got a negative charge, right? Because it just took an electron from sodium to make sodium chloride. And since sodium chloride just gave up that electron, it becomes positive, right? So sodium chloride is a sodium positive plus a negative chloride, right? That's just an example from what we've been using before. But there are plenty of other examples. The polyatomic ions are ones that are multiple, right? There are multiple atoms put together, and overall they'll have a charge, right? So here we have zinc sulfate. If you separate those two out, zinc's charge will be +2, sulfate's charge will be -2, right? Here is sodium acetate. Acetate has a charge of -1, and the sodium has a charge of +1, just like it does with the chloride. Okay. Magnesium here has a charge of +1, and then since there's two nitrates here, it takes two nitrates to balance out. Uh, Sorry, let me say that again. Magnesium has a charge of +2, and since there's a +2 charge of magnesium, you need two nitrates, right, to balance out the magnesium. That means that each one of those nitrates is one, right? Positive charge, -1. And then we have potassium phosphate again. You need three potassiums for every one phosphate, and that's because phosphate has a charge of -3, and potassium has a charge of +1. So you need three of those to balance those out, right? Don't worry, I won't really test you on how to figure out what those charges are, but you just need to see how they come together. Okay? I'm not going to say, here's an element or here's a compound, tell me what the charges are. I won't ask you that, okay? But you need to see how they come together as their names. Okay? So here's just a little tiny, not a tiny chart, but a big chart of all the charges I was just talking about. And most of the time, us chemists have to memorize this chart. you don't have to memorize this chart. But most of the time, chemists have to memorize this chart, and it's much larger actually for chemists. But so acetate here is the same acetate that comes from acetic acid, -1 charge. Bicarbonate, or also hydrogen carbonate, the thing that's a part of your bicarbonate, the carbonate bicarbonate buffering system in your blood, right? That's got a charge of -1. Hydroxide, which is a base, -1. Nitrate, -1. Carbonate, -2. Sulfate, -2. Phosphate, -3. -3. And ammonium, +1. Good stuff, right? You do not have to memorize that chart. It's just good to know that these different elements here, right, or these different polyatomics have different charges. Okay. So, which of the following compounds does not have a polyatomic ion in it? Okay. Which of the following does not have a polyatomic ion? What? Is it not scanning? Did it work now? Thank you. Oh, dang it. My bad. I'm Asian. I don't know my alphabet. Okay. So ignore that. I'm a little hard of English. If you hadn't noticed, I'm a little hard of English. English. You need some help, Derek? Got it? All right. All right. So what do you guys think the answer is? Is it A, B, A, or B? Which A? The second A, right? Yes. The second A is the one that is the not the polyatomic. So one of the things I want you to notice here, which is just so amazing, notice that all the polyatomics have 8 as their suffix, right? They end in 8, right? And the one that's binary ends in what? "-ide", right? So you don't even have to know what these things are. You just look at the name and you know whether or not it's polyatomic or it's binary, right? So I will ask you questions like that, though. You won't have to know like the charges. You won't have to know how to put these things together. But I will give you formulas or give you names, and you have to tell me whether or not they're binary or polyatomic. Okay? Does that make sense? It's pretty easy to tell. Pretty easy to tell. Okay, so then we have our acids, right? Acids are always the ones that have these extra H's, right? It's actually what makes an acid, this proton right here, this H, right? So hydrochloric acid is HCl, nitric acid is HNO3, acetic acid, which is vinegar, is HC2H3O2, sulfuric acid, H2SO4, carbonic acid, H2CO3, and then phosphoric acid is H3PO4, okay? So the only thing I might expect you to know, right, from something like this uh, which one is a binary acid, right, and which one is a polyatomic acid. So which one's the only one up here that's a binary acid? Exactly. Hydrochloric acid is the only one that has what? 2 elements in it, right? The rest of them have polyatomics on them. Make sense? Right? Cool, cool. The other trick here too, notice that all the polyatomics, right, all start with their actual names, like nitric acid, acetic acid, sulfuric acid, carbonic acid, and phosphoric acid, right? But hydrochloric acid, the only binary acid, what does it start with? Hydro. So all binary acids start with hydro, right? And all polyatomic acids don't start with hydro. Okay? See, because chemists are simple people. And we like to make patterns like that, especially for those of us who are hard of English, like me. And so that's an easy way to remember. Okay? So let's talk about, just naming some compounds real quick. Again, we have sulfuric acid here, which you saw a second ago. We got zinc carbonate here. This is a metal plus a polyatomic, right? I might ask you to do something like that. Figure out, is it a metal plus a polyatomic, or metal plus a non-metal, or whatever, right? Something like that. And then sodium sulfide right here, that's a binary compound, right? That's a metal plus a non-metal, okay? Silicon dioxide, right, which is, I think, is glass, right? That's also a binary, two nonmetals together, right? Ammonia, that's a special one. Don't worry about that too much. And then we have ammonium nitrate. Does anyone know what ammonium nitrate does? It's super explosive. Like you can use it to make like bombs and stuff, right? Okay. Really, it's the nitrate part. Like you put nitrate on anything, like nitroglycerin, kind of things. TNT, trinitrotoluene, right? All that stuff is like, bombs, bomb stuff. Okay. Not saying you should go out and get some nitrates and like explode it or something like that. I'm just saying, I'm just educating you. Okay. I'm just educating you. This is a very small chart. I can't even read it. Okay. Flow chart of naming compounds, right? It says, is it one of the 11 compounds with a special name? Oh, don't worry about that. Don't even worry about this because I'm not going to ask you to name anything. So put a big X mark on slide, whatever that slide is. Okay. So recall that the periodic table, that in the periodic table, each individual column is called a group, right? We know that already. And then all the elements of a group have the same number of valence electrons. We talked about that last week, right? For example, in group 7, they have 7 valence electrons, right? In group 6, 6 valence electrons. Group 5, and so on. Okay. If one element in a group reacts with a substance, the other element in the group usually reacts similarly. So we already talked about that before last week, where if you're in the same group, you tend to react similarly with other things. So I was telling you about how when sodium combines with chloride, there's like this little fizzling of an explosion that happens, and you get salt. The same thing will happen when you make potassium and chloride, right? Because potassium and sodium are in the same group. Does that make sense? So elements of the same group will react with other things very similarly. Okay? And we'll see that in just a second. And then the formulas of the compounds are created. What? The formulas of the compounds created are also very similar. We will discuss 4 of these groups. Okay, let's talk about those. All right, so, this is great. This is perfect because this actually cuts out the transition metals completely. It's beautiful, is what that is. Okay? And so we have this group here, which is the alkali metals, right? They have 1 extra electron, so it's 1 valence electron, right? That's why sodium is just so ready to get rid of its electron, give it over to chlorine, right? And then we have the alkali earth metals. They have 2 extra electrons, okay? And then as you keep on going across, notice that 1, 2, 3, 4, 5, 6, 7 corresponds to what? The number of valence electrons the element has. The group number is literally the number of electrons, right? The number of valence electrons, right? Not to be confused with the number of total electrons. The number of total electrons is in the atomic number, okay? But the number of valence electrons, which is the electrons on the outer shell that wants to be either given up or taking in to make a group of 8, right? They all have their valence numbers as a part of their group number. See, 1A, 1 valence electron, 2A, 2 valence electrons, 3A, 3 valence electrons, 4A, 4 valence electrons, 5A, 5 valence electrons, 6A, 6 valence electrons, 7A, 7 valence electrons. And then we have the halogens there and the noble gases with 8, right? Cool stuff. Cool stuff. Okay. So let's talk about the noble gases real quick, okay? The noble gases all exist as single atoms, like the monatomics, right? Because mono means 1, so they're monatomic, not like diatomic, like oxygen is or chlorine is, right? So all the noble gases, group 8, are monatomic. They almost never react to form compounds. Why would they? They've already got a full octet, right? Oh, by the way, we call that an octet. When someone has a full outer shell of 8 electrons, we call that an octet. Kind of like an octopus, but with electrons, so it's octet, right? And then so the noble gases have 8 electrons in their outer shell, except helium, which has a full shell with its 2 electrons because it's in period 1, right? And then 8 electrons in the outer shell is very, very stable. Neon signs contain minute amounts of various noble gases, and then when you pull an electric current through it, it glows. And so that's how you get neon signs, right? Argon gas is used inside light bulbs because even at high temperatures, it will not react with the tungsten filament. Did you know that? Did you know that the inside of a light bulb has argon gas in it, right? Because if it didn't have argon gas in it and it had regular air, the tungsten filament would just like corrode, like oxidize in the with the oxygen and the water in the air, right? So the inside of a tungsten light bulb, uh, or any normal light bulb, right, actually is either under vacuum or it has argon gas. Now, the other interesting thing too, did you know that your bags of chips? You ever wonder how what they fill your bags of chips with to make them poofy, right? They also fill them with argon gas too, right? That's why if you keep a, you can have a bag of chips, right, and it'd be expired for like a year, but if you've never opened it, it'll still be good. It won't go stale, right? And the reason why is because the argon gas is in there and it's not regular air. If there was oxygen in there or regular air, it would go stale because oxygen oxidizes the potato chips and that's what makes it go stale. But argon is there and it doesn't do anything with the potato chips, so you still have good potato chips right from the first day you bought them to like a year later if you don't ever open up the bag, right? Now, the interesting thing about this also is the fact that Oreo cookies, um, they last forever, even if you open them. So I still have a bag of Oreo cookies that I started back in undergrad. So, and I'm still eating them. So it's like one of those once every quarter type of things. I have an Oreo cookie, you know? It's like my treat to myself. I don't even know why I told you that. That makes no sense. Um, Lost my train of thought. Oh, argon gas inside light bulbs, right. So just to go through this one more time, remember that the alkali metals are here in group 1, and they all have 1 electron in their outer shell, and they're just dying to give up that electron. Please, please, chlorine, please come take my electron. I don't need it. I really don't need it. Okay. All right. So your next question is this: which of the following is not true about noble gases? They exist as monatomics. They almost never react. Noble gases have 10 electrons in their outer shells, or all of the above is true. Didn't mess up my alphabet there. Just saying. Just saying. Just saying. I think most of everybody has done their scan. What do we think the answer is here? It's C, definitely. It's definitely C because noble gases have how many electrons in their outer shell? 8, not 10. Okay. So let's talk about the alkali metals again. Let's talk about them ad nauseum, right? The alkali metals. Each alkali metal has only 1 valence electron, which I told you that many times before already. It tends to lose this electron, which means it becomes positive, and it will readily react with other elements. So they're very active metals, like sodium and potassium. They're quite abundant, whereas lithium and rubidium and cesium are quite rare, right? So reactive with oxygen and water that they must be stored in oil. That's why I told you a second ago, right? With sodium, it just explodes. Okay, that's why it's got to be stored in oil. Okay. So we have sodium chloride, which is salt. Some just examples here. We've got potassium carbonate, which is potash. I don't even know what potash is. I've never even. I mean, I know what potassium carbonate is, but I've never heard it called potash before. Anybody know what that is? What do we use potash for? It sounds like something marijuana type like. I don't know. Anyway, sodium carbonate, which is washing soda, right? And then we have sodium hydroxide, which is lye. You actually use lye to make those big pretzels. You actually wash them with lye. By the way, you didn't know that. I learned that on Alton Brown on the Food Network. By the way, right? And then we have baking soda here, which is sodium bicarbonate, which you can add to the acetic acid. It'll make you a fake, volcano, right? And then now you can predict formulas like potassium chloride or lithium carbonate, right? Because they all have very similar patterns. Okay. So contrast those alkali metals with the halogens, which most commonly they are partners of each other, unless these halogens like to do something incestuous. They're going to be they're going to be partners with each other, the halogens and the alkali metals, right? And again, the reason why that is because they fit so well to each other, right? 7 electrons, 7 electrons. Oh, just please give me that electron so I can put it on 7. We can have eights all the way across, eights all the way across, right? So a little some fun facts about the group 7 or the halogens, right? Each halogen atom has 7 valence electrons. They tend to gain an electron and readily react with other elements. So this actually makes them more negative. So they are very active nonmetals, right? They only occur in nature as a compound, but when they were purified, when they are purified, they occur as diatomic molecules like fluorine. That's the incestuous fluorine, the incestuous chlorine there, right? With two of them stuck together. Those are generally very poisonous. Fluorine is most reactive and will corrode platinum. Wow, I didn't even know that. I just learned something new today. All right, and I have a PhD in chemistry. Did you know that fluorine will corrode platinum? It's crazy. Keep your platinum rings away from fluorine. Okay, and cause wood, rubber, and water to burn on contact. Wow, well, that's crazy. Iodine is necessary for proper thyroid function. And so here's some other examples of these guys. Here we have aluminum chloride, ammonium fluoride, and then calcium bromide. Fun stuff there. And here is a picture of the three of them. Okay. Here is chlorine, which is kind of a green gas, right? Then we have bromine, which is kind of a red liquid, right? And then here's iodine, which is a solid purple stuff. Isn't that interesting, right? I would have we even when I was going through school, I thought that all of the halogens at room temperature were like gases. Turns out they're not. Crazy stuff. Crazy stuff. So, which of the following elements is not a halogen? Which of the following elements is not a halogen? I don't know about you guys, but I'm ready for this semester to be over. And I'm the prof. Uh, they always say that your first semester teaching is the hardest because after that you've got everything made already. Like all your exams, all your lectures, all your, you know. So you get into this old profs get into this like cycle of using the same exams over and over and over again. So I'm predicting I'm going to do the same thing. So same homework over and over and over again, same quizzes. Dang, that one person probably knew I was going to do that. That's why they took my class again for the spring. So anyway, I think everybody's scanned in, right? What do we think the answer is here, peeps? Who said C? D, yes, D. D is oxygen, and that is correct. That is correct. Oxygen is definitely not a halogen. So let's talk about the alkali earth metals now, right? Alkali earth metals are group 2, and as such, they have 2 electrons on their outer shell. They're happily able to give up those 2 electrons, right? Probably, most likely, to a group 6, right? Because it fits so well with each other to make 8. 2 plus 6 is 8, I think, right? And so it fits. Again, I'm Asian, I'm not good with math, but I think that 2 plus 6 is 8, right? And so group 2 elements tend to go with group 6 elements, right? Very, very interesting stuff. So some fun facts about the group 2 elements, right? This group contains 2 valence electrons, so they tend to lose 2 electrons. So they're generally charged as plus 2, right? Contrast that with the alkali metals, which is group 1. They become plus 1 charge, right? When they give up one of their electrons. They're not as chemically active as alkali metals, and they're generally stronger and harder, right? But they will still form, different compounds. For example, we have beryllium. Wow, that's hard to say. Beryllium aluminum silicate. Beryllium aluminum. I have no idea what that is, but its normal name is beryl. Beryl, whatever that is. We have magnesium oxide here, which is milk of magnesia, right? And then calcium carbonate, which is calcite. Calcium phosphate, which is in your bones and teeth. Barium sulfate, which is barite, and then um, strontium red and barium green give off colors. Oh, I got you. These metals here actually make red and green fireworks. That's cool, right? That's cool. And then we have Ra, which is radon, I believe, right? It's radioactive, radon chloride. Oh, I told you the story, right? How radon was used on watch dials to make them glow in the dark until it was understood that radioactivity was an issue, right? Because those women were painting the watch dials, and to make their paintbrushes straight, they'd lick their paintbrush and then dip it into the radon and then paint and then lick their paintbrush. Every one of those people died. It was quite sad. Every one of those women died of radiation poisoning, right? And the sucky thing about that is that this was like back in the 1900s when there was really no like worker laws, employee rights stuff, and so like there was no compensation or retribution for their families from the company that did that. They all said, "Oh, radon is quite safe," but it's not, right? I think radon is actually what killed the person who invented. Not I keep saying invented. The person who discovered radon was Marie Curie, and she ended up dying too. I actually visited her grave in France. It was nice. It was a good time. She has this thing called in France called the Pantheon, which is this huge thing that looks like like a Supreme Court building, but it's just her grave, her and her husband's grave. It's kind of cool. Anyway, I don't know why talked about that, but anyway. Um, Oh dang! That just reminded me of something. I forgot to put the picture of me and Röntgen's bust in the test. Next test, next exam. Remember Röntgen, the guy who discovered X-rays? Remember I went to his lab. I took a picture with his bust. I put my arm around his bust, and which was kind of ill-advised because the thing was like 200 years old. But you know, I said I was going to put that on the test, and you guys could say, "Oh, this guy discovered X-rays." You don't remember that? I remember that. We'll have to go back to the video, make sure. Okay. The good thing this is being recorded. Okay. All right. Oh, this is perfect. We're going to end pretty soon here, and then our three peeps who missed the exam on Monday can take the test. Um, so, lastly, we have hydrogen, which is usually in group 1A, but sometimes is in group 7A. Like I was saying before, hydrogen is the only nonmetal that's sitting on top of metals. Most of the time, though, we have it here, but it could really be over here. It could act as both, right? It sometimes acts like a halogen, so you get sodium hydride, calcium hydride. At room temperatures, it's colorless, odorless, it's diatomic. It's the lightest element and was used in early what? Dirigibles? What are dirigibles? Anybody know what that means? I have no idea what that means. No one knows what a dirigible is? Hey Siri, what is a dirigible?
An airship or dirigible balloon is a type of aerostat or lighter than air aircraft that can navigate through the air under its own power. Would you like to hear more?
No, thank you. It's an air balloon, right? So like one of these. This makes sense. I just learned a new word today, right? So the Hindenburg, right? Actually, so you know how you can fill up a balloon with helium and it'll float, right? Well, back then I guess they didn't think hydrogen was that bad of an idea to fill up a balloon with, like an airship balloon. And so instead of using helium, right, they used hydrogen. And of course, hydrogen is quite flammable, right? And the Hindenburg exploded. Is that 1937, I guess, in New Jersey? May 6, 1937, right? Good stuff. Okay, the very last question for today. Which of the following was not true about the alkali earth metals? This group contains two valence electrons. They're more chemically active than the alkali metals. They're generally harder and stronger than alkali metals, or all of these are true. And that is your last slide for today. All right, so what is the answer? What do people think the answer is here? B. Yes, that is correct. It is actually less chemically reactive. Okay. All right. That ends today's lecture. Thank you very much. Put your desk back together. If you have lab today, please stick around. If you have a test to take today, please stick around.